So we are very delighted to welcome Professor Swadhin Kumar Behra. He is Director Application Laboratory, GEMS Tech, Japan. And Professor Mukund Behra is also there with us today. He is Professor in Coral IIT Kharagpur. So we welcome both, and I would request our Director General to welcome Professor S.K. Behra and Professor Mukund Behra with the bouquet. So we again request our DGM to kindly felicitate Professor Swadhin Behra. Shall briefly introduce today's speaker. Professor Swadhin Behra was one of the 16 outstanding Indian scientists to give an invited talk to Honorable Prime Minister during the inauguration ceremony of वैश्विक भारतीय वैज्ञानिक वैभव, and he is a recipient of Vaibhav Fellowship by Government of India. Actually, this is a collaborative program of Department of Science and Technology, Government of India, and he is one of the meteorologists to receive this fellowship. And Dr. Swadhin Behra obtained his MS in Oceanography and Meteorology in 1986 from Behrampur University, Odisha. And we are very proud to say that he is a trained meteorologist from India Meteorological Department. He undergone 1 year advanced training in meteorology from our Meteorological Training Institute in Pune. He received PhD in Oceanography in 1998 and then moved to Japan for postdoc, and then onwards he is in Japan in serving in various capacities, and now he is director APL Jamstec Japan. He has received several awards and published a large number of papers, more than 150 papers in peer-reviewed journals, and he is also a life member of Indian Meteorological Society. So before we request Professor Behra to deliver his talk, I request DGM to say a few words.
Good evening, namaskar to all of you. On behalf of entire meteorological fraternity, on behalf of India Meteorological Department, Minister of Earth Sciences, and my personal behalf, I extend a warm welcome to Dr. Swadhin Kumar Behra, Director, Application Laboratory, Jamstec, Japan. And I express my deep gratitude to him for sparing his valuable time to be present here among us and for agreeing to share his views and knowledge, experience, or expertise for the benefit of the community and especially the young minds. I also extend a warm welcome to Professor Mukund Behra, Oral, Indian Institute of Technology, Kharagpur, for being present here graciously and sharing the occasion. As all of us know, Professor Swadhin Kumar Behra is a well-known figure, renowned figure, not only in India, but worldwide. And his specific contribution towards the field of meteorology and oceanography is known to many of us. He has been introduced by Dr. Soni briefly, but the ultimate, the outcome of his hard work, his perseverance throughout the year, starting from 1986 onwards. If you look at, there has been a huge contribution towards the science of meteorology and oceanography. He has also been a pioneer in recognizing India in the world in the field of meteorological and oceanographical research. He has been a pillar in developing the various supports and collaborations between Japan and India, especially in the field of meteorology and oceanography. He has been a supporter for many institutes within India and abroad for this purpose. It is really a golden opportunity for all the young scientists and engineers participating in today's program to learn from him not only about the science, but also about the applications and services which have grown over the years to serve the society and hence to maximize our societal activities and minimize the loss of lives. The talk which will be presented by him today, it is very contemporary, it is timely, And I'm sure it will invoke or ignite the young minds to take up further the research and developmental activities. It will also give some ideas to India Meteorological Department to further sharpen its services in the field of weather and climate. I just want to mention here that India Meteorological Department is celebrating 150 years of its establishment since 1875. We commenced our celebration on 15 January 2024, which was inaugurated by Honorable Vice President of India. Thereafter, we have taken off a number of activities in terms of the conferences, workshops, stakeholders interactions, publications, introduction of various logos, theme songs, etc. And above all, we are organizing a series of lectures by renowned personalities. And today, we will listen to Professor Swadhin Kumar Behera in this series of eminent personalities, lectures in the field of weather and climate and the applications to the society. Once again, I thank Professor Swadhin Kumar Behera for visiting IMD and agreeing to deliver this lecture. Thank you very much.
So I would request now Professor S.K. Behera to kindly deliver his talk on
Okay. Thank you, Dr. Mahapatra, DG IMD, for kindly inviting me here today. Also, Dr. Soni for kindly arranging it. It's a great pleasure for me to be here. As Dr. Soni mentioned, I took the training here, not in Delhi, but in Pune for 1 year. And that was a kind of foundation for me to develop my research, because the foundation was based on understanding of atmosphere, dynamics, physics, including synoptic meteorology, forecasting. And those were kind of helpful for me to generate my career in research based on the basic understanding I got from India Meteorological Department. And today I'm happy to share our thoughts and views on climate action through digital twin innovation. And I would like to recognize Bhagava Fellowship, which Dr. Soni mentioned and Dr. Mahapatra mentioned. I'm a Bhagava fellow working in India. My host is Professor Mukund Behera in IIT Kharagpur. And I'm working in India since July 29th. And this fellowship gives me funding to stay in India at least for 1 month. So I'll be here for 1 month. And with Professor Behera, we have been doing a lot of research on understanding how climate influences vegetation and its impact on society. But we are trying to do the reverse way. There is a big vegetation, forest and irrigation land, non-irrigation land. And it must be having some impact on the climate. So we are trying to understand the other way. It's a kind of chicken and egg thinking. So maybe rainfall is helping vegetation, but later vegetation will also influence the atmosphere and rainfall. So that kind of positive feedback we are trying to understand using whatever observation we have and what the models output we have. And hopefully we'll have some idea how monsoon reacts to the vegetation. There are already some preliminary studies, but we need to understand how the fluxes from the forest and ecosystem is influencing the monsoon. That's what we are trying to study. Next slide, please. So as you have seen here and you have experienced this year, we had a long, prolonged heat wave over India. And I think the not WMO, the UN Secretary General already said that we have gone beyond global warming stage. Now we are in global boiling stage because the heat waves are getting very intense, and you might have experienced already this year. And also it is lasting for longer period, not only in April, May, which used to be in my childhood, but now we can also experience heat wave in June, July, August. So that's kind of problem for the society, and we need to address that. In addition to that, we have seen forest fires and the floods and the droughts. And in order to address them, we need to understand how they are linked with climate and other factors. Next slide, please. So in this slide, you can see that some of those extreme events and extreme weather events, they are some way or other, not all of them, but most of them are linked to what we call ocean and atmosphere climate phenomena. These are like El Nino, the Indian Ocean Dipole, the El Nino Modoki, even monsoon. They are kind of ocean atmosphere interactive systems like phenomenon. They last from a few seasons to like 1 year. El Nino lasts even more than 1 year. And in that way, they become kind of anchors for extreme events. Through their teleconnections, they influence the extreme events. The heat waves, the floods, the droughts, all are somewhere or other linked to this kind of climate phenomena. And why we are looking for these climate phenomena? Because the extreme events are kind of noisy systems. They are difficult to predict. Some of the extreme events we may predict 2 or 3 days ahead, but then we don't have enough time to take actions. And the mitigation measures, if you want to establish, we need these things to be predicted sufficiently at long lead times. So that's why we try to understand how they are linked with climate phenomena, because these climate phenomena basically driven by the heat in the ocean, which are slowly propagating boundary state. So because they are slowly propagating, they are easier to predict and more reliably we can predict them. So that's why if you can establish the link between these extremes with climate phenomena, and if we can predict the climate phenomena, which we are good at this time, then we have a hope that we can also predict, at least probabilistically, we can predict those extreme events sufficiently ahead of time so that the society can be prepared to take actions. Next slide, please. Now, these kind of extreme events are not confined to land only. They are also seen in oceans, especially the marine heat waves. They are becoming also very intense, and they are also becoming long lasting. And marine heat waves directly or indirectly influence the human society through the food chain, also through other factors like how the ship routes are established, and also they influence the weather systems, nearby weather systems. So in that sense, the marine heat waves and extremes in the marine, in the marine systems, like the storm surge and extreme waves, freak waves, that also need to be predicted sufficiently ahead. And we are trying to establish how they can be linked to climate phenomena. Easily, everything is related to climate change. People will think that everything is because of global warming, but not necessarily we can directly connect global warming with extreme events. That's why we have to take into consideration this middleman like the climate phenomena and how they are linked to climate change and also extreme events. And next slide, please. Next slide, please. And for that, we know that we need the modeling, we need the observations, we also need smart interface to provide the information to the society. And that, if we combine together the observations, the modeling, and the interface, if we combine together, that can be a kind of digital twin, which is already known in engineering fields, like building ship, building jet engines, already being used in industry. And those are kind of digital twinning of real processes or real machines and mechanisms. In these engineering aspects, it's easier to develop digital twin because we have set of equations and we know what parameters we have to fine tune. So it's much easier to develop digital twin for engineering aspect. We hope we can extend that to environmental aspects, including ocean atmosphere interactions. and also ocean variability and atmosphere variability. But we know there is infinite degree of freedom for ocean and atmosphere, and sometimes it's not easy to set parameters, and our understanding is still lacking because we don't have enough observations. But nevertheless, the UN Ocean Decade, which started in 2021 and will continue until 2030, they have come up with 10 challenges, starting from marine pollutions to policy decisions. And challenge 8 is digital representation of the oceans. So in that, this digital twin came up as one idea in challenge 8. So digital twin started for the oceans, but now we know that digital twins we need for atmosphere, we need for climate, we need for local weather, we need for urban planning, everything. So it's kind of expanding now. But the basic idea is we need observations, we need good models, and then we will, on top of that, we'll prepare a good interface. I think the support systems we are creating in many centers is somewhere linked to the interface. So in that way, we can develop the digital twin. Next slide, please. When we talk about the observations, we are still trying to progress in that direction. We still need a lot of observations, both in land and the ocean. At least over land, we have a good observational system in India and in developing countries and developed countries. In Africa and other places, still it is lacking, but we hope we'll catch up. For the ocean, we don't have enough observations compared to land, and we need to improve on that. On the modeling side, we have come up a long way from the toy coupled model developed by Suki Manabe and Cork Bryan, led by, I think, Von Neumann and also several others. And as you can see, in 1960s, Suki Manabe and Cork Bryan, they developed the toy model for the Atlantic. And that toy model was able to capture the Atlantic overturning. So encouraged by that, we had a lot of progress in ocean atmosphere modeling and coupled modeling. And today we have, I think, several centers in the world have 10-kilometer global coupled models. And that is giving us confidence that we have a better component on the modeling side to be part of the digital twin. Next slide, please. At Jamstack, we are doing coupled modeling since 2005. We started the coupled modeling in collaboration with several European centers, Max Planck in Germany, Lausanne in France, and INGV or CMCC now in Italy. And the models we used, ECAM for the atmosphere model, OPA for the ocean model. Now it is NEMO, well known as NEMO. And it was coupled by Orca, developed in France. And the model was doing well to predict, at least simulate El Nino and Indian Ocean Dipole and the SST variability in most part of the world oceans, at least 3 months ahead. On right, the top figure shows you the model skills. So wherever you see yellow and red, and those are skillful predictions. And then we start from 3 months, 6 months, 9 months, and 12 months. So in between, you have 6 months and 9 months. You can see the skills have reduced in most places, but we still have good scale in tropical Pacific and Indian Ocean, which is most important for monsoon prediction, at least. So in that sense, we are doing well, and this model is doing well to predict El Nino, Indian Ocean Dipole, and to some extent, monsoon indirectly through those climate phenomena. And hopefully, some of them also captures the extreme events. Next one, please. We have been continuously improving this model. We started with Syntax F1 with 100 kilometer. It comes 4.6 and OPA 8.2 at that time. Then we improved to ECAM 5.3 and NEMO. And the third one, we are now using ECAM 6.3 and NEMO 4. Eventually, we will go to icosahedral models so that we will be able to increase the model resolutions. At the moment, the F3 is like 40 to 50 kilometers in the atmosphere. and maybe 60 kilometers in the atmosphere and 25 kilometers in the ocean. It's good enough for like climate simulation, but still not good enough to kind of simulate some of the eddy scale activities, like the ocean eddies, which are a few kilometers length. We are still not at that stage to resolve eddies and also resolve cloud in these models. We have dream at some time in 10 years, probably we'll have 1 kilometer atmosphere model coupled to 1 kilometer ocean model, resolving most of the eddies and probably some of the clouds. And we are far behind that now, but even then, this model is quite good enough to predict El Nino, the Indian Ocean dipole, and to some extent monsoon. Next one, please. Not only we are improving the model, we are trying to also improve the subsurface assimilation systems and increase the number of ensemble members. Now, the Syntax F2 has 125, 26 members, ensemble members. What we found that the increasing number of ensemble members is not improving the ensemble mean. We take the 126 members and make just arithmetic average. And that's how we get the ensemble mean. And what we found, whether we have 50 members or 120 members, the skill has not improved a lot between 50 members and 120 members. However, we found that if you are going for probabilistic forecast, we have at least 20 to 30% increase in the efficiency skill of models. So in one way, it's like we continue with the deterministic forecast, but at the same time, deterministic forecast is what stakeholders want. We try to work with many users, including industries. They always ask for a deterministic forecast. For example, we work with the Tokyo Electricity Company. They kind of bring a lot of gas, and I'm doing the time. It's okay. So, so they need to predict temperature sufficiently ahead so that they can plan how much gas they need to buy, because that price also is fluctuating, and if they don't plan well ahead, it's quite a lot of money. But then working with them, we realized that they have not developed their skills to be able to take probabilistic forecast into their models. So all the time they want to ask us, they just ask us, what will be the temperature in July? What will be the temperature in August? Absolute value. So we have to give exact value, which should be correct for them to be able to predict how much gas they need. And we tried for several years, but eventually we are not successful because they are not able to use our probabilistic forecast. So there is a need now for this to train stakeholders how to use probabilistic forecast. One thing is we create predictions. The other thing is how it is used by the users. So we found some gap in what we are giving and what the user wants. So that intermediary stage, I think we need a lot of improvement. We are trying to do that now through the digital twin. Next one, please. Yeah, that's fine. And this one is the prediction, just to give you an example of what we have been doing. The model is able to predict El Nino and IOD and to some extent monsoon, I told you before. And this is the example of prediction given on 1st August for the September, October, November global surface temperature, sea surface temperature, and the prediction of Nino 3 index and the dipole index. And to tell you the truth, now the model is predicting a La Nina state and the negative IOD states, which we are observing already. The left and the right bottom figure is observed sea surface temperature from NOAA, just taken now. So you can see that the Indian Ocean, like western side is getting warmer, eastern side is getting warmer, western side is not so warm. So kind of negative dipole kind of thing. And the La Nina is developing now, which model is predicting to be even stronger in September, October, November, and will be further strengthened, I think, by December, January, February. But to tell you the truth, the model was flipping from negative dipole to positive dipole and positive dipole to negative dipole for last 2-3 months. And this is very strange for the model, but it has never done such thing like changing the prediction 1 month after 1 month. It predicted, I think 2 months ago, it predicted positive IOD, then is negative IOD, again positive IOD, then negative IOD. So we are trying to understand why model is doing that. Sometimes the models are overconfident. They capture one side of the signal based on what signal they have from the subsurface and the wind field and the rainfall. And which says that we still have a lot of room for improvement. Nevertheless, we are doing okay if you take a long time average, we are doing okay to be utilized for the society. Next one, please. One thing is to improve the model, and the next thing is improve the ensemble average. So to improve the ensemble average, I think we found that there are several machine learning methods we can use to improve the ensemble average by providing weightage to better ensemble members. It's not necessarily that all the ensemble members are bad. Some ensemble members do consistently better. So we use here two different techniques. One is the genetic algorithm. The other one is selective ensemble mean. Selective members we pick up from their consistent skills in predicting temperature, especially in the mid-latitude regions where the skills are low. We found that by selecting ensemble members or using some machine learning technique, we can improve the skills of predictions. Same predictions, but by just changing the way you are averaging them, we get some skills in the predictability. Next one, please. One thing is the dynamical or the numerical climate predictions, what you have seen. The other way is to use deep learning, machine learning, or AI to predict. So far, we try to solve the equations, primitive equations by using numerical techniques, by converting partial differential equations to partial difference equations. That's what we have done. That's what I was trained. And I spent most of my life in that. But what I'm seeing now, the same thing can be achieved through statistics. These are statistical models trying to establish the relationship among different neighboring points. And based on that, they try to predict what will happen in the future. They kind of establish some network, neural network, by connecting points. And then based on that, they predict what will happen in the future. Some of the machine learning models are black boxes. We cannot understand why they're, of course, the models might be predicting better than dynamical model, but we will not know why they're predicting well. But some of the deep learning models like CNN, convolutional neural network models, they have feature maps. So from that, we say heat maps. From that, we can diagnose why that model was able to capture some of the variabilities and able to predict them well in advance. So I think if you are going into the machine learning and AI kind of work, probably you should choose some of the gray boxes, not the black boxes, for your own understanding, to understand the physical processes. Otherwise, you will not learn anything. It will become like same kind of thing. The machine will predict and we just follow them. In this case, we are using the deep learning to predict ENSO. And we found that for longer lead times, the deep learning model based on CNN is beating all the dynamical models we have in the world. So for 18 months to 24 months, the model has scaled like 0.5, now even increased to 0.6, whereas most of the dynamical model, numerical models are not able to predict beyond 12 to 15 months. Next one, please. We also found similar thing for East African rain. The model, CNN based model was able to predict East African rain. much better than the syntax F or any dynamical model. And we are doing that also for monsoon and other regions. And we also want to use the same technique to predict monsoon rains based on these models are basically dependent on sea surface temperature and heat content. We can add more variables to that, like surface pressure, wind, and other things. But we are also trying to do the same thing using vegetation. That's one area is what we want to do together with Professor Behera is to include vegetation in this kind of models and see if we can improve the predictions of monsoon, for example, in this case. Thank you. Next one, please. Now, the AI-based weather and climate predictions are becoming more like industries are taking up them more better than what researchers we are doing. You already know maybe NVIDIA's model. It is beating NVIDIA claims they are doing better than ECMWF predictions. But then they are taking ECMWF analysis as the initial state. So without good ECMWF analysis, I don't think they can do predictions. So one thing is to claim that AI is predicting, but AI is also based on analysis and observations. Without good observation, good analysis, no AI model will give you predictions. That we should not neglect. The monitoring system should be good. The analysis should be good so that the AI model can learn, and it should be sustained for a long time. Then the AI model can learn, and from that we can predict future easily. NVIDIA and Google, they are quite advanced now. And in China also, they have developed several one. Fengu is one of the model. 1 kilometer resolution here, they are giving very good skill predictions based on only AI machine learning. And also the climate models. I have seen several climate models. Now they are developing based on deep learning. Transformer technique, there is another technique like CNN, transformer. And transformer model can predict two-dimensional. Even CNN can predict two-dimensional fields. Like what I have shown you before is index, but they can also predict two-dimensional field like SST, rainfall, wind, completely based on deep learning technique. No dynamical model in that. So that is quite promising, and we should think about those things as well, besides the numerical models. Next one, please. And I said that digital twins are dependent on 3 factors. One is observation. The next one is model, including AI models. I only talked about the deep learning models, but some of the models we are developing now is completely AI. AI in this sense, they are developed based on large language model, like ChatGPT. So ChatGPT has API, and we can use that API to ask ChatGPT to optimize our models. So ChatGPT will use all the information available to it, and it will select which model it will pick up. Not necessarily CNN, not necessarily ANN, not necessarily random forest. It will pick up based on its own understanding. And we found that that is far better than our selected AI models, because they're already trained and they know which one is working better. And they're so smart, they work directly from your Python code. In the Python code, you just put a comment. I want the model to pick up this feature, and ChatGPT knows what to do to pick up that feature. That's the state we are now. So we don't have to learn any of these AI models, any of this. We can directly use the large language models like ChatGPT. And those are not trained for ocean and atmosphere. They are still general. Once we have the ocean atmosphere ChatGPT that many centers are developing now, I think India also should develop. And if that is developed, then we will be far ahead, far ahead. We don't have to depend on anybody for like preparing the code based on one single machine learning model. And then the interface. So once you have good model, you have good observations to train your models, then you need a smart interface. I think decision support systems are already there in many centers, and IMD also has one. And at Jamstack, we want to develop what we call the 4-dimensional virtual Earth. At the moment, it is just 2-dimensional. It is not smart yet. We want to make it smart. It's not smart yet. It's still 2-dimensional, but it's just beginning. And eventually, in next 7 to 8 years, we will develop it in a way that it will become 4-dimensional, both horizontal plots and also the vertical sections, and with time animations. And then it will pick up everything smartly. We just say something, I need this and this, then it will automatically create the plots, what you want, based on your understanding and your need. Hopefully it will be ready in next 7-8 years, and hopefully same thing will also be developed in India and in other places. Thank you. Next one, please. One thing is to develop this kind of digital twins. The next thing is what is its use. And most of the users are now based on smartphones. So we want to create contents and also develop skills to be able to predict the things which society needs. Next one, please. So we work with several, next one, please. We try to develop several applications. One of them is the health application. One thing is the heat wave predictions. We are doing that. And we want to actually collaborate. We also talked to DG and also Dr. Pai sometime back. And we want to collaborate and try to see how we can develop the early warning system for the heat waves. One thing is to predict heat waves based on temperature. The other one is to integrate with vegetation and the ventilation system. So each city has its own ventilation system. And most of the cities in India and also elsewhere, they are not planned properly to ventilate the heat. We are creating heat island, it's fine. But if you also can establish a good ventilation system, create a corridor so that the heat will be passed, then I think we can cool the cities at least several degrees so that we can reduce the impact of heat wave, also reduce the cost of energy. That's important for the society. That's what we are trying to do. Then we are also developing malaria, dengue, and all other health-related models. So most of them are AI, machine learning-based models. Of course, there are also physical models, but we found that physical models are more difficult to manage. How to fine-tune the parameters, how to put the observation into that, those are really challenging. We worked with the bacteria, I think, for the mosquito predictions, but it was not so successful. AI machine learning models are doing better, and that's what we are trying for malaria and dengue. And this is one area also where we can collaborate because IMD also is working on those disease-related models. Next one, please. And of course, agriculture, and IMD is very much related to that. So we found that by coupling the climate model with agriculture model, we are able to predict the yield of many of those cereals and also even fruits and vegetables. So we are trying to develop further onto that. And eventually we'll be able to provide forecast. At the moment, most of the forecasts are used by rice farmers and wheat farmers. Wheat farmers in Australia and rice farmers in Southeast Asia, they use regularly our predictions now. But we want to expand on that and try to improve the skill scores so that it can be used by many farmers all over the world. Next one, please. And this is the one I'm working with Professor Mukund Behera in IIT Kharagpur under the Vaibhav Fellowship. We want to, this is the first stage where we established how the climate is influencing the vegetation. The next stage will see how vegetation is giving back to the climate and up to what extent. I think that will depend a lot on the observations because the atmosphere is kind of highly sensitive to the amount of sensible heat, to the amount of latent heat, to the amount of evapotranspiration. Those are going from the vegetation to the atmosphere. our understanding at this moment is that the irrigation has helped a lot to improve the atmospheric vapor moisture. And that in turn is helping to increase rainfall over India. Vegetation, the irrigation is already helping. We need to know now how forestation or deforestation is kind of changing that dynamics, and how much is in the northeast India, how much is in the northwest India, and that kind of thing we want to study through sensitivity experiment. And here again, we need the support of IMD to get the observations, because we need high resolution observation for that and for a sustained long period. So hopefully we can establish some kind of collaborations for understanding vegetation impact. We know already SST, how SST influences climate, how heat content influences climate, how soil moisture influences climate, but vegetation role is not so clear, and we want to study that. It can be another field for prediction. Next one, please. Next one, please. So one area we are developing, and the atmosphere one, the other area also we are developing similar digital twins for the ocean. And for that, we already have established ocean models. And we are also developing digital twin for the ocean based on the ocean predictions. And it's also the UN Ocean Decade program. And this is the model we are using, Japan Coastal Ocean Prediction Experiment. It has high scale. And now we are trying like 200-meter all coastal region of Japan. Once we are successful, then we will kind of expand that to Southeast Asia. And together with INCOIS, I think also we can do that for the whole Indo-Pacific domain. That's what we are trying. Next one, please. And this will be part of digital twin initiative taken by UN Ocean Decade. And we have a program called Digital Twin of the Ocean, and I'm presently co-chair of that. So I'm trying to propagate that idea to all ocean atmosphere related fields, so that we can have more user. This digital twin concept is like you develop, it's not one digital twin. We say digital twins of the ocean. So we can have a small Bay Area digital twin, and once successful, that can be integrated to the global system. That's what we are planning now. Next one, please. And for Asian region, we are developing this Asian hub, and with so many interest in that, right from ocean observations to policy decisions. And hopefully it will be established in next few years, so that the countries which cannot afford for good modeling centers or good observational centers can be benefited from this kind of regional hub. Next one, please. And this is the framework we want to develop. We need to first establish what is the technical framework for the digital twins, and then develop a community around that, develop capacity, and collaborate with other Ocean Decade programs, so that the decisions and actions can be taken together, and we can share our information with stakeholders and get the feedback from them. Next one, please. This is the plan we have now, like digital twin of the oceans can be used for both blue economy and coastal systems, and to address several kind of societal issues, from fishery to navigation to kind of recreation and even rescue operations. And hopefully the digital twin you're developing now can cater to many sectors of the society, and eventually will be helpful to large population. Next one, please. So this is the conclusion. So we already know something about the ocean atmosphere, but we need to do more, try to improve our understanding. And that we can do by improving our monitoring systems and sustain it for a long time. One thing is to do a very dense observation system But then if you don't sustain it for a long time, it is not very useful for both validation and also assimilation. So that's why we need dense observation. At the same time, it should be sustained for a long time. So it will help both numerical model, also the AI-based models. And hopefully by doing that, we will lead our society. Now we say we are in society 4, we are going to a society 5, and hopefully we will develop better models for next computing system. When I joined IITM and trained in IMD, we still are working on card readers. We used to send cards to Mumbai TI for, they used to run the model and then say, okay, you have compiler error, compiler error. Then the person comes back again, send another packet next day, then we have another error. But then we moved from card readers to tape readers. We are reading several megabytes 1 hour. And now we are in petabytes, petaflops. So hopefully we'll go to the quantum systems where you can run the model in, if not in meter scale, but at least in kilometer scale, and help the society in that way. Thank you.
Thank you, Professor Behra, for a very enlightening talk. We can take a few questions. So, good. Is there any?
Tony?
Yes.
Dr. Pai.
Yes.
So in fact, very excellent lecture, and you have touched so many aspects actually.
Yes.
From ocean to climate and technological and feedback between your vegetation, what do you call land cover, land
Yes.
change,
Yes.
cover change, aspect with the monsoon. But I will limit to one or two questions. One is you said that in the this year there was a flipping of
Yes.
IOD because
Yes.
that is interesting to
Yes.
most of the people might have noticed.
Yes.
So is it that is it that of the regions specific artifact of the region that the year-to-year variation of SST our Indian Ocean is very less
Yes.
compared to Pacific when you go.
Yes.
And you have got a value also, you will see that 29, 30 is almost in the
Yes.
equatorial.
Yes.
So this actually, small variation can in fact go to positive or
Trigger,
negative.
trigger.
I'm just
Trigger can that. Yes.
and another why I said artifact is that you have got an Indian monsoon. One is coming from branch coming from Arabian Sea,
Yeah.
another from Bay of Bengal.
Bengalis.
So this will have, if Bay of Bengal is strong,
Yes.
it will cool your east
Yeah.
Indian Ocean.
Yes.
And if it is in the Arabian Sea, if just flipping, and this is a very natural aspect of monsoon.
Yes.
Sometimes your Arabian Sea branch is stronger, Bay of Bengal branch is stronger. This may have got impact. So really the question many times I used to ask is whether is it IOD is an artifact of monsoon or IOD is actually again chicken and egg problem. When monsoon is very strong, you will find a positive IOD kind of thing. So just to understand that, that is one point. You will clarify that. And another, when you said AI is going to replace many of that. So I'm some kind of not agree, problem in the sense that see AI just getting observation around without physics and what is happening interaction. I don't think that AI is going to enter physics is going to generate simply just observation.
Yes.
If you train that how that is going to totally simulate all the aspect which is very complex in the nature, because nature itself I was telling you that is a totally random process. Nothing is not depend on previous, though we say that many times it is a random process. How an artificial intelligence can generate those type of random process to give you an accurate forecast. And finally that chart CPT which you GPT which you said unless you trained you have got a good knowledge, you may make a mistake also, because you whatever available information which will be best and then you will pick up, whereas human he will have know that much better. And I'm just saying this aspect, many other point also you touched upon. And similarly your land sea land cover, it was continuously changing. Land sea cover, how frequently that you should need an update you will generate a real simulation, the impact, and it can really simulation get an output. And what is the technology readily available? So even when satellite and other thing that you talk about, they are all good, large extent. Again, many of the climate impact that we will see that it's a local impact rather than a global impact locally. Have got to move. These are just my doubts, and maybe you will be able to shed more light on that.
Okay, so 4 questions. Starting with IOD, whether IOD is generating monsoon or monsoon is generating IOD. I tend to believe it is IOD because IOD is a tropical climate phenomenon, dependent on tropical dynamics, the Rossby waves, the Kelvin waves, and those are kind of driving the SST and the air-sea interactions. Monsoon is a large-scale system. While saying that this is a tropical phenomenon may be happening because of tropical dynamics, I don't deny that there should be interaction between monsoon and this. As you said, we have 2 branches, the Arabian branch and the Bay of Bengal branch, and the flip-flop I'll come later. Those large scale can influence the IOD, but what we have seen is IOD start developing in April, May, and then goes to peak stage around August, September. So during June, I think June to some extent, July, one could be leading the other. Sometime maybe the IOD is leading monsoon, monsoon may be leading the IOD. The large scale may be leading the tropical one. I will not deny that. But the September, August, September, October, the IOD is fully established. And the cooling on the eastern side will affect the eastern side, Bay of Bengal branch definitely. In that sense, whenever you have a positive IOD, so we wrote that paper again, when there is a positive IOD, the monsoon trough gets stronger. So central India gets good rain in the positive IOD. But it's not necessarily that in the negative IOD you will have less rain. In the negative IOD case, the western side monsoon gets activated. So you have a dipole again, east-west dipole, not north-south, east-west. So western side get more rain, eastern side get less rain. Because the eastern side, most of the rainfall is confined to the Sumatra region because the temperature is higher there. So most of the things get struck in the eastern side. The eastern side doesn't get so much of rain, but the western side is fine and they get more rain. Gujarat, Rajasthan, they get a lot of rain during negative IOD years. That's what's happening this year. And in that sense, I think it's chicken and egg. Some sense, I think IOD is kind of more climate kind of dynamics, whereas monsoon is large scale dynamics. Some people say land sea contrast. I don't believe that much, but maybe there are some other factors, including vegetation. I'll come to that. And then coming to the flip flop, as you said, it could be triggered by the SST variations. And SST variation in Indian Ocean is lower than the, especially central tropical Pacific. And this year it happened that central tropical Pacific variation was very high. So that might be triggering one sense or the other in the model world. At the same time, Western Indian Ocean is getting warmer. The trend of warming is much higher in the Western Indian Ocean compared to the Eastern Indian Ocean or Pacific. So in that sense, Western Indian Ocean is kind of creating a mechanism which doesn't change the positive kind of IOD quickly. So it model try to pick up positive IOD every year. So if there is slight indication in the Western Indian Ocean, it quickly turns to the positive IOD. That's another factor. One is Central Pacific, the other is Western Indian Ocean. That flip-flopping is happening in the model world because model doesn't understand what is going to dominate in the next few months.
So that is the bias or?
That's bias. That's bias. Model bias. And then the second question, I forgot. Second question is AI. Both 2 and 3 questions are related, ChatGPT and AI. So one thing is to use AI as a black box, I said, and that's what most people are doing now because it's difficult to interpret. But I believe in like gray boxes where you can understand some part of it, if not full. And the second thing what we are saying is physics oriented AI, physics interpreted AI. There are two things. Physics oriented AI, where it will still be a black box. But if you are saying physics interpreted AI, that is where you are trying to tweak what is happening in AI. So that's why I said the comments. So in the comment section, you can put, okay, this is the random signal I know which helps this kind of event. So then AI will pick up and try to train based on what input you have provided, based on your understanding of the physics. AI doesn't understand the physics. You are providing the physics. Your interpretation you can put as comments. Then AI will pick up from that. Eventually, AI will learn from your learning. It will not know it is a physics, but it will know that this is what it wants to do.
Say for monsoon prediction, so you will give something like IOD, and so.
IOD, and so you can say monsoon trough, how monsoon trough behaves. You also have local system. Local system. So try to find local system from the cloud. And if you find some signal, okay, try to predict that. And then time scale, of course. And ChatGPT is right now not prepared for ocean and atmosphere. So many centers, including ours, we are trying to develop ChatGPT for ocean and atmosphere, for climate. So those will be exclusively for us and based on our physical understanding. In that sense, we can put our understanding of physics into those models. That's what is happening now. But eventually, those will be black box. Like the next generation, next to the next generation, they will not know what understanding we had, what physics we put, because everything will be in those large language models. They will be already included. Our understanding of the physics already will be included in the ChatGPT. So I'm worried about the next generation. Maybe you people will know, but next generation will just use them as black box. Maybe those will be available on their smartphones, so they can directly use. So that is the problem. Next generation, how to teach them the physics we understood. Then the fourth question is how vegetation will influence, because it is rapidly changing, as you said. But we have several parameters now which we can observe from the satellite, remote sensing. One is GPP, the other one is SIF. Even we can sense the transpirations, respiration happening in plants. And based on that, we can develop some of the index, global index, which can be related to atmosphere and rainfall. Of course, land is changing, land use also is changing. And that is rapidly changing in the Himalayan regions. And how much you can put that in the model, I think that's a question. But at least the Northeast India and the Northwest India, where we don't have so much of change, that part I think we can do. The foothill of Himalaya, those things I think we can do something.
I was looking at this weather and the weather and climate extremes, as you know, that maybe top 1 percentile of the event or 5 percentile you take. Is there any research publication that we have seen that any extreme prediction is challenging? So what about this AI ML? Are they talking or discussing on this issue, predicting the anything?
You mean probabilistic forecast? No, 5 to 10%.
As you told something like, what is the chance that the temperature will be, top 1
extreme
percentile?
events.
Yeah, extreme, not the highest value, but like some values in that side.
Percentiles in
some value that side, because highest rainfall like 100 centimeter is not possible in weather model. Also a month like, very excess rainfall may not be possible. So what about this present technology? Like
AI ML are doing better in that. So when you are going to extreme event in terms of percentile, we found that between 50th percentile and 75th percentile, the chances are better that AI ML will predict better than dynamical models. But when you go from 90th to 100th percentile, like 95th percentile, and those are the challenging areas too. We need further improvement for that.
Most of the extreme rainfall,
93%.
this one is a 95, 99, 99.9.
The models are capturing their phase very well. It can say, okay, it will start probably in this time, and the probability of in the seasonal prediction, probability of which week we will have more extreme event. That way they are doing very good. Even Nino 3 prediction they are doing very good. The problem is the intensity. Most of the AI machine learning model, like dynamical model, they are not able to predict the intensity at all. Maybe 30% of the intensity.
So I learned a new terminology, like you told, among the ensemble member, there are few members, they are
Selected
doing
members,
good.
yes.
So that is a good approach, I think.
Yeah, selective member averaging is better actually.
So that's it.
The finding good members consistently is the problem.
Mm.
That somebody has to spend time to pick up.
That may differ.
That might differ from model to model. Yes.
And in his lecture, he also mentioned a very important point. Mid-latitude predictably is very less compared to tropical. So many times we think that they predict much better. Seasonal prediction is not that much good than what we do in tropical.
That's why you can convince Indian government to get funding because predictability. Our government is saying, okay, your predictive skill is so low. Why you want to spend so much money?
Yeah, why? Because there the pattern is stagnated in some season or month leading to.
That's it. Mostly
The
frontal
better.
systems. Yeah.
Short range is better.
Short
But
range is
not
better.
the
Sometimes
season.
the pattern also persists for longer period, making the anomaly higher.
Yeah.
Is it like that?
It's like
I mean, your monthly variation in the middle latitude for any, say, rainfall over Japan, the monthly variation, the standard deviation is very high, or like our monsoon did only 10.
standard deviation will be high because mostly it's dependent on the events.
Day-to-day events are much
Frontal
higher.
events, synoptic scale events, those are difficult to predict on seasonal scale because those are mid-latitude systems dependent on the easterly waves, westerly waves. We know that if it is happening in the China or Siberia, it will come to Japan next.
So you cannot tell every year normal like us.
But if you want to
Monsoon we
predict that next month, you cannot do that.
So like us, we tell many times monsoon normal. So because if you do the average, it will be.
Mean knowledge always you are good. The only problem is standard deviation.
Yeah.
You want to?
Yeah, just actually couple model what your friends few tests that is version 3, that the latest one. No? So that is slightly better compared to senior brother. You also was showing one SST prediction 36 month. That is statistical.
Statistical model.
So my point is whether climate model what was not still the statistical and ANN is the AI models also now equally doing good. So whether we have reached the upper predictability limit with the climate model?
You mean statistical model or dynamical model?
The dynamic model.
I think we have already reached that stage. The next thing we want to do is like kilometer scale models. That's what we are debating now. Whether kilometer scale in several centers, we wrote a paper on that. Kilometer scale means it will be confined only to big centers. Not all centers can do that. The other one is the AI machine learning based model. You still have 10 kilometer resolution, but use AI machine learning to improve your prediction.
Yeah, so that means that means further improvement of climate.
Please, there is still scope.
Yes, sir.
There is
Yes,
still
sir.
scope. There is still scope.
You have to do yes, sir.
Yes, there is still,
Absolutely.
Complete.
including AI machine. Still further scope is there, but we cannot reach 100%.
Yeah,
That is for sure. That is for sure.
Any question that works?
My question is, digital twin is a representation of real life to digital
Yes.
model.
Digital.
So, in case of your study, how you represent this digital real world in the digital twin in oceanography?
So
Next question is, sir, is this applicable for other forecast, for example, fog forecast, thunderstorm forecast, and in that case, how we can represent digital twin in the real world to digital model?
digital models. So digital models are kind of representing ocean and atmosphere. And for the long time, I showed you Suki Manabe, who got the Nobel Prize for doing that. So Suki Manabe, Corcoran, they started couple modeling, ocean modeling. Corcoran was doing ocean modeling, and Suki Manabe was doing the atmosphere modeling. At that time, people didn't believe how the radiation works, how this thing, and they developed the schemes for that. So that's why they become pioneer. In that sense, they already brought the real world into the virtual world, computer world. So they are the pioneer in the digital twinning of atmosphere understanding. What we are doing now, digital twin doesn't mean only the models, but also it should include all the available observation into it. So we are trying to integrate observation into these models and then create a nice interface so that who is not knowing about the ocean atmosphere modeling, they still be able to use it. That's the idea. So digital twin is kind of providing services or ocean atmosphere models to everybody in the world. Anybody who can use the monitors, they can also run these models. That's the idea.
So we can use it.
You can also use it for forecast or even any other forecast. So that is your digital twin. Depending on what you need to do in your forecast, you can develop that digital twin.
So if in case of as a layman, from where we start it?
For the atmosphere, for the fog forecast, I think you just need the atmosphere. So if you have a good atmosphere model, and on top of that, you add AI machine learning based on the observations, and that will become your digital twin. And you set many parameters, and the user can make what if scenarios. What if temperature goes up? What the maximum temperature is high? How much moisture you need for this? And those kind of parameters you can set, and user can click those parameters based on their need, and then they will forecast whatever they want. That's what this is.
Any questions in chat box? You can read.
When you say kilometer scale model, is it a global one? What is the resolution, deterministic or ensemble, coupled or atmosphere only?
So what we are discussing now is 1 kilometer global coupled models, deterministic forecast. That's what we're discussing now. Well, of course, there are statistical models which they are also trying. I showed you 2 of the models in China. They are also doing 1 kilometer resolution global, but those are statistical models.
You can read the name of the questioner. Fine. Other question?
So I have a question, sir.
Yes.
Especially when we do digital twin model. So we have to do a bench, right? So here in my case, we are applying for the urban scale applications. So we are developing one downscale bench at 300 meters for Delhi, for suppose. So cities like Delhi, so what we are doing, sir, is a combination of digital twin plus discrimination. So in the discrimination, to compute the loss, so I have more black boxes here than the gray boxes. So where I have to hit more, sir? That's the main question for me.
If you purely go for operational purposes, black box is also fine. But if you want to understand and write some research paper, then gray box is necessary. Without that, you will not understand the physics. So depending on your need and demand, like DG asks, okay, give me this forecast. Then you will not see gray model or black model. You will just give the forecast.
One more question, sir. Especially in the digital twin, we have to take the support of NWP models also. So especially when we go for these meta scale models, predictions actually. So that time what we are facing is when we compare the loss with the observational bench, the loss is sometimes very randomly it's getting very high and very randomly it's getting very low. So even after applying some filters kind of things also, some data sets are still going on wrong way. So is there any suggestion that you could give to us?
There are 2 things from our experience, there are 2 things you can do. One is hyperparameter tuning. You must be doing that. So there are several techniques to fine tune them. If one is not working, you can try the other one. There are established 2, 3, I think you can try them. That's one thing. The second thing from our experience is number of observations you have, the time series of the observations. If you have a long time series, you don't get so much of variation in errors. So sometimes that's the biggest problem. You don't have enough data, and then the model are not confident to train themselves, or they're overconfident in training in one direction. So that's why you get more errors. So those 2 things I think help you.
Okay, thank you.
One hand is raised.
SK, but Bhattacharya.
Thank you, sir. Sir, I have a question on the AI prospect of AI models capturing rarest of rare cases, because under the climate change scenario, we are more concerned about the rarest of rare cases, extreme events. So since the AI models are not that much trained with those data, so what do you think about the prospect of capturing the rarest of rare events by the AI model?
Yeah, thank you for asking that. And that is the tricky one. So rarest of rare events, we are not trying to predict now using AI machine learning. We are not doing that because we know even if you're successful on the hindcast to capture those rare events, it's not necessary that you will be able to predict in the future. Even if you are predicting in the future, the confidence on those predictions are very low. The AI machine learning model based on actually the number of events. So if you don't have sufficient number of events, most of the time the models will, even if they are trained well, that is not, it's not necessary that they will be able to predict in the future. So that's still an area where I think dynamical model can be more reliable.
Sir, I have one more question. I have an idea, understanding rather, that may be wrong. I would like to correct myself on this. But I think that feeding with data and the past events data rather, AI model is kind of going with the climatology. What do you think about it?
Sorry, I could not pick up the last part.
AI model is going with kind of climatology, or climatology means, predicting things so with what happened in the past, rather correlating things. So what do you think about that? Means if I'm wrong, please correct me.
He's telling, recalling, climatology only, what has happened in the past.
Yes.
Is it like that or anything?
AI model is kind of means relying upon the climatology, means kind of thing.
Not necessarily. AI model is only linking the points. Like neurons, it's taking several layers of neurons, and it is creating, mostly it's based on a high level of correlation and regression. Basically, all the numerical model, all the NN and CNN models are based on that. So it's kind of establishing some kind of links among the points, and from that it finds the most probable patterns that emerges, and from that it tries to predict, okay, if this is the scenario, the pattern which will come out is like this. So that's what it is doing, not based on climatology necessarily, but the climatology may be integrated into the system based on those neighboring point correlations or far point correlations.
See, perhaps his question may be, if you take, old historical data, if some extreme events are not there,
it will not capture.
No, but AI is trained without that. Can in the future something happens, a new event, and which was not there in the historically, whether that will be able to predict, like your even regression method also, same problem comes.
I agree with that.
I told that they are also linking to different coordinates, like wind may be taking, not alone the rainfall is taking. Suppose I need rainfall prediction. I will look into the rainfall related parameters, or I will only click rainfall past some scenario or something.
Taking more variables. Taking more variables is better. Then you have more parameters to train.
Only looking,
just one parameter is not enough. And then the question is, if there is no extreme events, whether the model can predict the future extreme events. Some people claim that. I don't have any experience to say that, but some people claim that it still can predict. They have experience of predicting that. Yes.
So, thank you,
Thank you, sir.
Professor Behra, for nice talk and then a very
I'll just
interactive session.
any our young scientists. Okay, Raghu has asked. Any other young scientists ask a question? Yeah, Saban.
Yeah. Thanks. Yeah.
So, for example,
advantage in the past. But when it comes to extreme rainfall events, the intensity of the rainfall. So,
Yes. So your question was? It's just comment, right? Yeah, I agree with you. And the science, as you said, and AI can produce the science itself. We already have the technology. I think some of the papers you send to journals, they are now checked by AI. So no human beings are checking. They say it's in the editorial office, actually it is checked by AI. And they found that actually some of the editors told me, nature editors told me, when they use AI to assist the authors to produce, to kind of rewrite their papers, they found often those papers get accepted easily. So the raw paper coming from some of the authors who are not native speakers, sometimes they're rejected because they are not written well. By taking help of AI, they found that that can be improved. And there is a more chance. There is more chance for those papers to get accepted. That's one thing. The second thing I have already seen, AI can write your papers. It's already happening. It's already happening. Yeah.
Can give a better language actually.
Yeah. And you know that already the AI is preparing the code for you. You have specific demand, you just ask, prepare the Python code for this, and based on this, it prepares you the code. It's already there. So writing paper by AI is not far away, I think.
But it takes the idea from the human being.
Of course, you will say what you want to do. Of course.
yeah. Dr. Ramesh,
So
you can come here near the mic.
machine learning has many algorithms. In many of the algorithms, around 99% of the algorithms have the proofs. Whereas deep learning came into the picture as a dark box. Initially, the deep learning is depending on CNN. That is started in 1976. So handwritten recognition mechanism. So how these automatic features are going to be extracted does not aware. So many of the people are thinking that the deep learning is going to be taken as a dark box, and they will give the input, they will get the output. So the main funda out there is in machine learning or AI or earlier mechanisms, we are supposed to say that what kind of features need to be get from the images or a text or whatever the input. But the deep learning is not depending on that automatically extracting. Now the trend has been changed, as you know, as you told also, transformers came into the picture. Understanding of the transformers is up to 90%. We are able to identify from this state what will be going to the next state. That kind of dialect has been specified from the transformers. So they have gone to the LLM and as well as this ChatGPT and all the things they have gone through that. So that means now my perception is what the deep learning is. Initially it started as a dark box. Now it is become like gray box, and it's giving more scope. And these transformers are there, and many of the people and everyone is thinking that the artificial intelligence, that means deep learning, is thinking that mapping between the input to the output. And if you're coming to that, especially this atmospheric and input output mapping, it's recently, so we have a few papers, you have put one paper over there that is forecast. They have solved the partial differential equations there. So that means if we are talking about if you are taking that NWP model, there also we have the solving of the partial differential equations, and these equations we are solving with the help of the supercomputer with a large number of the data. That can be done using this. So this Anamika Kedar, she is from the Google, she is doing that 4-year learning concepts that implemented. Yes, sir. And recently in the June end, that means 24th of the June, that Google DeepMind has released one paper that is neural GCM. That is basically depending on the computational of this partial differential equation, and that becomes the now. And Pongu is also done. They have done with the help of the 3D transform. That
and model understanding is also somewhat easy, and they are depending on observational data and data only. So that means rare event is the only one point we
Yeah,
need to
well,
put.
Yeah, some people are already claiming that we can capture rare event.
Actually, a few instances with the help of DGs are also success that we came to know that we have set of events. And if any rare event happens, that rare event we can give it to the model in such a way that in future, if any such kind of rare events is happening. So that means giving the input again, that modifying the model automatically by itself. So that trend.
Yeah, so as you are discussing, like 1995 we can still capture what 99%.
You are working in that direction.
Right.
This is our AI man.
Okay, yeah.
Yes, please. Shukla.
Dengue and malaria using AI/ML. So that can you just tell us how, what are the
For the malaria, we use the DLNM model, lag nonlinear model, and it's a kind of lag regression model. One model is that, and that model was able to capture malaria several weeks ahead. Scale is like 0.8. And then we also developed a AI machine learning based model, which is using several AI techniques from random forest to support vector machine to several other models. And they're not ANN models. They're just ANN or CNN, just simple machine learning models. And based on that, what we found, we are not able to predict malaria weeks ahead, but we are able to predict malaria months ahead. So these models, AI-based models, they are able to predict malaria like 2 to 3 months ahead with a scale of more than 0.7, 0.8. So there are two types of that lag nonlinear model and the AI model.
What are the difficulties for now?
Dengue, now casting of
Any kind of like
for malaria and dengue and even diarrhea, we did the same thing. We need hospital data. Observation is very important. So luckily we had malaria data from South Africa for 20 years. So that helped to train our models. If you're not getting sufficiently long lead time, long time series of data, threshold data for any health related diseases, I think it will be difficult to develop an AI model. That's the first thing you have to do.
Yeah. Yeah. Again, Sonali, you just come.
Yeah,
He's another AI person.
sir, actually, it was very fascinating that you showed that IOD prediction using that syntax model.
Yes.
So, do you have any validation for how many years IOD and like it has been predicted?
So based on all the past observations and these things, so that's what I showed you one figure. I think it was not so obvious. The scale of IOD prediction is not so high compared to El Nino.
Yes.
And the lead time is only 3 to 6 months. So 3 to 6 months ahead, the scale is above 0.6, which we think skillful, which we regard as skillful. Anything above 0.6. So IOD is good up to 3 months or 4 months ahead, not beyond that. But ENSO, we can predict 12 to 15 months ahead.
Actually, ENSO prediction using this machine learning technique, it is for a long time people are
Yes,
doing.
yes.
Because IOD actually prediction is not that common, like it
Yeah.
has just started, I think.
Yes.
Jamstack itself, it has
Yes.
started. I don't know.
Yes, we already did that, and several other groups also did using CNN transformer technique. And those are also like that. 3 months, 4 months ahead prediction skill is high, not beyond that.
No, yeah, and actually I was asking, is there any validation like for how many positive IOD it has?
Yeah, for last like from 1982 to present, all the events.
Okay, fine.
Yeah, all right.
Another is a very general question I'm asking. See, do you think that using, as you are talking about this ChatGPT, so using this ChatGPT that will reduce researchers' innovative skill for the young generation at least, because for a true modeler, first job there is to study the science they are going to model. And then they use, it is a, very basic, skill,
Yeah.
like which has to be developed, like to use the techniques to model the thing. But if the ChatGPT does that job, then the researcher skill is going to, especially like then they cannot,
Yeah.
like innovate a new technique for that.
So as I said, next generation, maybe they will not do that. But your generation, still you have to do it because as I said, ChatGPT is following your instructions. And you have to say something in your comments. And that is what we say physics interpretable AI. So if you know the system, you know where you need and what you need. Like you can say, okay, you know that SST in the Pacific is important for the prediction of El Nino and IOD. And you say give more importance to this region's SST in all the predictions. Optimize the model based on this. And still you will control that. But in future, I don't know what will happen. Maybe those control will also go to ChatGPT. At the moment, still you can control based on your physics understanding.
Because one job of the machine learning mathematical modeler is that to innovate new techniques also.
Yes,
new machine-
yes.
improve the technique also. So that thing will
Yeah, eventually it will take over. I agree with you.
Thank you, sir. For
Sir,
this,
questions?
still,
Yes, sir, two more questions are there.
Only
One is any plans to develop an end-to-end AI-based model like GraphCast or Pangu or Forecast at IMD?
in IMD.
Andy, your question.
Progress. Yeah, work is in progress. We are trying to do something in line with Pangu weather or the GraphCast. And a group has been constituted within IMD. There is another group within Ministry of Earth Sciences. Also, we have gone for collaboration with various institutes like IIIT, NITs, and IITs. So, attempt is on for development of various modules for various purposes, like for nowcasting, rainfall predictions, temperature predictions, cyclone forecasting, and in general, of course, development of models based on certainly what Professor Behra told is the analysis field of ECMWF, which is being attempted at present by IMD.
Next question is, sir, you pointed to quantum computers. When do you hope it may be applicable in meteorology and climatology?
Thank you for asking that question. I somehow didn't cover that well. When you come to quantum systems, it's completely different from the binary computers we are using. Binary computers are dependent on like yes or no, 0 or 1. So you have many if statement inside your Fortran codes, and that cannot be used in quantum systems. Quantum system operates on two things. One is quantum gates. It doesn't have binary system, quantum gates. And then the final solution is not like absolute value. It gives a quantum state. At the end of your solution, you get a quantum state. And not necessarily your numerical equation will give you the same quantum state if you repeat that for several times. So what people do is they run the models or run the equations for several times, 100 times, 150 times, and then take an ensemble average of all of them to get your quantum state, which you think is corresponding to your results. That's what people are doing now. And for ocean and atmosphere, we started working on that. Particularly in my group, we are working on a one-dimensional wave equation, just one-dimensional wave equation. Very simple equation. We can solve that numerically. You can solve that analytically. And what we found right now, the quantum, we have two types of compilation. One is quantum gate. The other one is quantum annihilation. And we found that quantum annihilation is working for us. Even then, the solutions are not guaranteed that will be always correct. At the moment, they are doing worse than the binary computers and taking more time. But eventually we think, as he was telling, like we are solving partial differential equation using AI technique, transformer technique. So I believe the transformer technique and the Python code will help us to use the quantum computer to solve all our model equations, ocean atmosphere equations. And I think in next 5-10 years, we'll have a rapid development for that. After 10 years, things will be much better. At the moment, we are struggling.
Thank you. And for this very nice interactive session. Now for final comments, I would request our DGM to say a few things. I'm sure that after seeing this discussion and presentation, there is a lot of scope for collaborative studies and further research work. So request DG to kindly comment on this.
Yeah, so thank you very much, Dr. Soni. At the outset, I express my deep gratitude to Dr. Swaden Kumar Behra for very illuminating and inspiring talk today, covering various aspects of weather and climate science, its monitoring and prediction processes of various types of weather elements, and especially focusing on the tools and technology, including the twin, digital twin. He also highlighted the future technologies which will be adopted gradually by the various countries. And we feel proud that the Son of the Soil has made a mark in this field, in the global arena. When we talk about the IOD, or we talk about the digital twins, or we talk about the applications in the field of health or water sector or DRR. He has also spelled out the opportunities available for collaboration between India Meteorological Department, other organizations, Ministry of Earth Sciences with Japan. We should take advantage of that. I feel he has tried to ignite your mind. All the youngsters, those who have participated in this program, they have come to know about the current status of the tools and technology, the current status of the predictions, how challenging it is to predict the extreme weather, and what are the scopes further to convert these challenges into opportunities. And I am sure, just like he went giant or we went giant in beginning of 90s, what are the challenges? And if I just go behind and compare today with the days in 1990s beginning, there has been a paradigm shift in almost all aspects. The concept itself has changed, and outcome has been that we are now able to predict most of the severe weather events, even if, say, a few minutes before or a few days before. And we are able to predict at present the status of the climate, even a few years before. It has certainly enabled the society and the individuals to minimize the loss of lives, and of course, the optimization of information of weather and climate in their day-to-day life, and hence socioeconomic activities. But still there are challenges, and he has put up all those challenges and how it can be solved further by utilizing the data available, by utilizing the technology and further development of the technology, and by utilizing the human knowledge along with the artificial knowledge, that is artificial intelligence. The human intelligence cannot be ruled out, cannot be avoided. Even if you go for application of the physics-based AI, there you need the interpretation, the intervention by the meteorologist. So we feel really very enthusiastic after listening your talk. It has certainly helped and enabled all the young scientists in IMD and other parts of the globe, those who are participating in today's program. I thank you very much for sparing your valuable time.
So we request our DGM to present a memento to Professor Behra to keep us in his thoughts.
Always. Yeah. You just remember that IMD is now 150 years old. Thank you. Thank you. Congratulations. Hello. Yeah, you can declare that now.
Yeah. So finally, I thank Professor Behra, Professor Mukund Behra, and all of you for sparing the time. I can see our very senior member, Dr. R.C. Bhatia ji also who is listening us. And so thank you all for sparing your valuable time for this lecture. And very soon we'll come up with another talk under this series of 150 years talks. Thank you. Thank you.
Yeah.